Welcome to Experience 5. This is the end of the unit. So we've been talking about orbitals, and it's a really abstract concept. To try to picture electrons alone is hard, but now we're picturing them as existing in these little bubbly regions around the nucleus where they have a high probability of being found, and these regions have different shapes and sizes and energy levels. It's kind of a lot. I feel like at the end of Experience 4, you're probably left being like, I have no clue what just happened. I am lost, totally lost. But that's, I think, what we're going to try to fix in Experience 5, that we can bring this full circle. And I know you're going to be like, oh, I get it. Okay, so if we go backwards a little bit, I'm going to backtrack to these bubbly orbitals. So here were all these shapes of bubbly orbitals. The s orbital is a sphere, and then we had the p orbitals that were these dumbbell shaped, and the d's had like a clover leaf shape, and f's are even more crazy with 8 lobes. And we kind of said, the difference between a 1s and a 2s is just that it's a larger spherical region, because 2 means the second energy level, and that's a little farther from the nucleus. And then the same could be said about any of the other orbitals, that you could have a p orbital in the second energy level or a p orbital in the third energy level, and it just is a little bigger, dumbbell shaped. Each orbital can hold 2 electrons max, and we try to fill orbitals lowest energy to highest energy. The number of electrons that can fit in an energy level is just dependent on the available orbitals in that energy level. Okay, so at the end of this Experience 4, there was a question on revising our explanation going back to the firework thing. Rather than saying the electrons transition between energy levels to produce colors of fireworks, because that's maybe our previous Bohr model was saying that if I add energy, electrons can move to a higher energy level, and then they fall back down to the ground state to be more stable. How might you refine the description using your knowledge of the quantum mechanical model? That's this orbital stuff. What does this tell you about the energies of the orbitals? And so again, these are just kind of like what you think. You're just trying to revise your model. So there's not necessarily a right or wrong, but maybe you were just kind of thinking that now if I add energy, the electron's not just moving to a higher energy level, but it's maybe moving to a higher energy orbital. Maybe I'm moving from like the 1s orbital to the 2s orbital, or the 3s orbital. Or maybe I'm moving up to a 3p orbital. That now we know that there's more than just these energy levels, that within the energy level there's different regions where we have high probabilities of finding electrons, and those electrons are still free to move amongst the energy levels and the orbitals that would exist in that energy level. But here's the deal. You will never ever need to draw orbitals. You will never have to draw these clover, dumbbells, spherical regions. You don't have to draw those. But we do want a way of mapping out where all the electrons are found in an atom. Eventually, the electron structure is what we are most concerned about. In chemistry, chemical reactions and bonding are all about changes in electron structure. And so I want a good way of coming up with like a roadmap that shows me where the electrons are located and where they might be moving to. And realistically, like going back to this picture, like it's kind of a roadmap. Or I could say, the first 2 electrons go in the 1s orbital, and then next I would put electrons in the p orbitals, and then I should say 2s, and then I'd go to the 2 p's. And then eventually I'd have D's and maybe F's. And so you could draw something like this and put the little dots in the bubbles. And I guess that kind of gives us a good visual on exactly where the electrons are located and what shaped regions they move around in. But who's going to draw this, right? Nobody's going to draw that. Although this is really what I'm like kind of picturing in my mind. we need a better way of modeling what's really complex, something that's a little more usable. And for that, we have something called an electron configuration and an orbital diagram. This is where it's going to get really good. Okay, so electron configurations are just a way of showing the arrangement of electrons in various orbitals around the nucleus. But instead of having the exact shapes, we're just going to show the orbitals as a box. And I get it that the s orbitals are not boxes and the p orbitals are not boxes, and here when I have these boxes it looks like they're all the same shape and size, and I get that they're really not. But this is way easier to draw than like bubbly three-dimensional structures. So we're going to show the orbitals with a box, and then we're going to show the electrons as arrows. And we kind of mentioned this in a previous video. When we fill the orbitals, both the orbital diagram and this thing called an electron configuration show how electrons are arranged in the subshells, which just means like the orbitals, starting with the lowest energy and then moving up to higher energy levels. So we always fill orbitals low energy to high energy. Always, always, always. And so, for example, if I'm hydrogen, I can look in the periodic table. Hydrogen has 1 electron. We're talking neutral atoms, so if the atomic number is 1, then there's 1 proton and 1 electron. Okay, well, we're always going to start with the 1s orbital, and since there's only 1 electron, we'll just draw 1 arrow in the box for the 1s orbital of hydrogen. Cool. That's called the orbital diagram, where we show arrows in boxes to represent where all the electrons are distributed. You can also shorten that a little bit into what we call an electron configuration. If I can find a better color than this. What'll stand out good? Maybe orange. No, not orange. Where'd my purple go? I like that purple color. There it is. Let's go purple. Okay, so here is what we call the orbital diagram. Here is what we call the electron configuration. They kind of show the same information, and there are times when I like one better than the other. There are times when I like them both. The electron configuration is just another short way of showing the same information. So number one, the orbital diagram is a lot easier than drawing three-dimensional bubbles. But then the electron configuration is even further a shortcut, where we write 1s, 1 referring to the energy level, S referring to the shape of the orbital. I'll write that here too, 1s. So the first symbol is going to be the energy level. And then you'll have the letter SPDF. That's referring to the shape of the orbital. Shape of the orbital. And then finally you'll see like a superscripted number. So if I see like 1s1, that little superscript tells you the number of electrons in this orbital. So it's even shorter than the boxes. So if I see 1s1, it means that there's 1 electron in the s orbital, first energy level. So I would know then that this is an electron that's really close to the nucleus. It's in a spherical shaped orbital. Pretty cool, huh? And then so on. Each time we add an electron, we just put another arrow in the box. Now we can still have up to 2 electrons in each orbital, so maximum of 2 arrows in a box. And when I do have 2 arrows in a box, I show them spinning opposite directions. We have 1 arrow pointing up, 1 arrow pointing down. And so for helium, the rule is that you can't move on to higher energy orbitals unless you've completely filled the lower energy orbitals. So I can't put an electron in the 2s until I go back and finish the 1s with 2 electrons. So So for helium, we show 2 arrows in the 1s going opposite directions, and its shortcut electron configuration would be 1s2. That's the only available orbital in the first energy level, and then that's why the first energy level only holds a maximum of 2 electrons. When I go to lithium, now lithium has 3 electrons, so I would put 2 in the 1s, and then the third electron goes in the next available orbital, the 2s. And so then lithium's shortcut electron configuration becomes 1s2, 2s2. Oh. And can you kind of note on top, like up on top here, they're showing like the symbol of the orbital. And the first box represents the 1s orbital, the second is the 2s. And I get that in real life, like the 2s would be the same shape but a little bigger, but that's just not something that we're going to show with these orbital diagrams. And so on. So, beryllium has 4 electrons, so it would be 2 electrons in the 1s, 2 electrons in the 2s. But now the 2s orbital is full. So when I get to boron, I'm going to put the 5th electron in the 2p. But we always fill low energy to high, so we always start with that 1s, and then we just keep going, filling 2 electrons in an orbital until we get to something like carbon. So carbon has 6 electrons, and I would fill the 1s. I'd fill the 2s. But now in here, this is kind of where things get a little funky. We mentioned this rule. It's called Hund's rule. You don't have to remember that. It's not on any test. But Hund's rule says that when you get to equal energy orbitals, so for example, like p's and d's and f's, where there are 3 p orbitals here, and they're all equal energy. They're just lying on a little different axis in space. Their orientation is a little different. We should fill these equal energy orbitals 1 electron at a time. Electrons are negative, and like charges repel. And so if I don't have to put them together, I'd rather not. This just makes the atom more stable, and we're always concerned with atoms being stable. So we're going to separate the 2 electrons in carbon's p orbitals and give them their own orbital. And it's like, you got 3 bedrooms, you got 2 kids. Give them their own room. They won't fight, right? And then we've just got one of the p orbitals that's empty. Now, technically, it doesn't matter if you put your arrows up or down. If there's only 1 arrow in the box, it doesn't matter. Just if you have 2 arrows or 2 electrons, they must spin opposite. And technically, we don't really know which p orbitals are filled. So, I mean, you could put the arrow in the first box and the third box. Usually, we just kind of go down the line and put 1 arrow in the first box and 1 in the second box. But they're all equal energy, so technically it doesn't matter. Now when I get to my electron configuration, we just keep listing the orbital, and then we put the number of electrons in those orbitals as a superscript. So with carbon, I would say 1s2, then the next orbital is the 2s, and that has 2 electrons, 2s2, and then we go to p2. And so we put this as 2p2, showing that there's a total of 2 electrons in the 2p orbitals. But now here might be a case where sometimes I like the orbital diagram, because yeah, there's 2 electrons in the p orbitals, but sometimes I like to know, well, how are they arranged? And in the end, it's kind of important to know that, ooh, these are in their own orbitals, and that might affect the way that carbon interacts with other elements. He's got some empty spots in those orbitals. And the same thing when you get to nitrogen. Nitrogen's 1s2, 2s2. That takes care of the first 4 electrons, but now I've got 3 more, so they just each go in their own p orbital. Ah, cool. That's the most stable way to put 3 electrons in equal energy orbitals. Give them all their own. Again, we show the electron configuration as just 1s2, 2s2, 2p3, but I like to sometimes see the visual that shows me that those 3 electrons are actually in their own orbitals. But now here's where things get a little different. When you have oxygen, and you've got 8 electrons to fill, we fill the 1s with 2, the 2s with 2. That takes care of 4. Now I have 4 more electrons, but only 3 available orbitals, 3 p orbitals. Well, the rule is that you have to fill the low energy orbitals before you can move to a higher energy orbital. So with oxygen, I would fill 1 at a time, but then somebody has to get paired. I've got 4 kids in 3 rooms. Sorry, someone's going to have to share. But you can't go up to, like this guy. Here's I'm oxygen. So here's oxygen's 3s. You can't go up to the 3s until you completely fill the 2p's. You can't jump to higher orbitals. So you've got to go back and pair 2 of the electrons. Now, it technically doesn't matter which ones you pair. Usually we just go with the first. But now here's a good example of what's wrong. So this is oxygen. This is going to be wrong. Sad face. Okay, so let's say I'm in the p orbitals. P orbitals. 1, 2, 3. Sometimes you might even see like a little symbol underneath that shows these are all equal energy, and they are the 2p orbitals. Here they're kind of showing us way up at the top. Let's say I'm filling these. It would be wrong to do this. 1, 2, 3, 4. Sad face. This would not be stable. This would not be a stable arrangement because I've got more repulsion than what's necessary. I've got this empty orbital. Why wouldn't I want to use it? So they could give you something like this and trick you, and then we'd want to say what's maybe wrong with this configuration and why. And that we would say that, no, we wouldn't want to pair more electrons if we don't have to, because they're going to repel each other. I mean, like charges repel, and that would then not be stable. Same thing happens with fluorine. Now with fluorine, you're going to need 5 electrons in the 2p orbitals. So with fluorine, then the most stable way of putting 5 electrons in 3 orbitals is to have 2 pairs and 1 single. Oh. Neon, with 10 electrons, will actually fill the 2p orbitals then. All the orbitals are full in neon. And then after that, if I'm sodium, now I can go and put my last electron in the 3s. Sodium with 11 electrons would completely fill the 1s orbital with 2, the 2s orbital with 2. A total of 6 electrons would go in the 2p orbitals, and then electron number 11 would start the next available orbital, which that's it for the second energy level. Then I would jump up to the 3rd energy level. Okay, kind of okay, getting there, maybe. And at one point, your science teachers probably told you that the second energy level can hold 8 electrons, right? Yeah, it's because of the available orbitals. The second energy level has an s orbital, and then it has 3 p orbitals. And each orbital can hold 2 electrons for a total of 8. Ah, cool. All right, so this is a good example of 2 different shorthand ways of showing how electrons are distributed in an atom. And I like them both. For different reasons, I like them both. We talked about this role of energy in trying to make particles stable. Electrons will always occupy the lowest energy subshell or the lowest energy orbital first. That's why we always start with the 1s, and then we move to the 2s and the 2p and so on. If you've got subshells or energy levels where there's more than one orbital, And 1 electron then will occupy each orbital before pairing. So this is all referring to like the p orbitals and d orbitals and these weird f orbitals. We fill them one at a time and then we pair if they're equal energy. And we mentioned the spin thing, that when you've got these moving charged electrons, they create a little magnetic field around them. And it seems most stable then that when they're in an orbital together, they'll spin in opposite directions, and that kind of helps to not neutralize their charge, but it helps to minimize any extra repulsion when they have to be put in an orbital together. And so again, here's just kind of an example of where we would start with these electron configurations and orbital diagrams. First, you got to look at the periodic table to figure out how many electrons we're dealing with. So if we were looking at oxygen, we would find the atomic number to be 8. 8 protons, 8 electrons. Then we would start with the lowest energy orbital, the 1s. We'd fill it with 2 arrows pointing opposite. I don't really do this. I don't really ever do that step. I just start right here. I start putting my arrows in. And then I know that I fill the 1s with 2, then the 2s with 2, and then when I get to the p's, I fill them 1 electron at a time, and then if I have to, I'll go back and pair them. So like if these were my p orbitals, let's say that these are all of my 2p orbitals. I fill them 1 at a time, so let's say it is oxygen. I'd go 1, 2, 3, up. I need 1 more, 4. And eventually it would look just like this. That then is called the orbital diagram. And from there, if you want to convert that to an even shorter way of writing this, so you don't have to write boxes and arrows, which I guess would be a little annoying if you ended up with like Mercury or something that's going to need 40 boxes and 80 arrows. You can write the name of the orbital, 1s, 2s, 2p, where the first number is the energy level, the second is the shape, and then the number of electrons in that orbital gets written as a superscript. We read it as 1s2, 2s2, 2p4. Oh, I love these. So for example, let's try one. Looking at the role of stability in filling these orbitals. We fill low energy to high again. And I think we covered a lot of this. We covered the electrons spinning in opposite directions. We covered the 1 at a time when we get to the P's and D's. Here's this yogi guy, I guess, some yoga master. If he were to fall to the ground, he would have less energy, and his new position would be more stable. Low energy is always more stable, and that's the whole point of all these rules in filling the orbitals. We're trying to put the electrons in the most stable configuration as possible. Let's do 28. This is where I think it's all going to make sense, I hope. We're going to apply the concepts of energy and stability as they relate to orbital filling to write the electron configuration for iron. Okay, so often they'll have the boxes written for me, so I don't have to draw the boxes, and they'll even have them like kind of paired together properly. So whenever there's an S, there's only 1. Whenever there's a P, there's 3. D's, there are 5. Notice that, you know, we would go first 1s, then 2s, then 2p. That's it for the second energy level. We usually think we should then go 3s, 3p, 3d, but they've snuck the 4s in there on you. It's okay. We'll deal with that in a little bit. But it just is that we feel overall lowest energy to high. I think we kind of mentioned it, that even though the 3D orbitals are a little bit smaller, they're higher in energy. D's are just crazy high energy orbitals, and there's 5 of them. So they've got the boxes all set for me, and they're right. So now I just need to know how many electrons am I going to draw. So I look at iron on my periodic table. Iron is number 26. So I'm going to need 26 arrows. So we start at the beginning and then we just work our way to 26. So I would have 1, 2, 3, 4. Technically, when I get to my P's, I like to go 5, 6, 7. Well, for sure I have to pair them. 8, 9, 10. I can fill the 3s with 2 right away because that's the only orbital at that energy level technically. So now I'm at 12, 13, 14, 15. I need to pair them. 16, 17, 18. I can fill the 4s right away. 19, 20. And then here's more equal energy orbitals. So I'm going to go 21, 22, 23, 24, 25. And number 26 is going to have to get paired. It doesn't technically matter which one you pair. I mean, usually we just go with the first one. But that would be the most stable arrangement of 6 electrons distributed amongst 5 orbitals. We try to evenly distribute them as much as possible to overcome from any repulsion of negative electrons being close to each other. Now technically this would be called the orbital diagram. When they ask for the electron configuration, then we can just take these symbols in another shorthand way. 1s, there are 2 electrons. 2s, there are 2. Then the 2p, there's a total of 6 electrons. Then I had the 3s for 2. The 3p had a total of 6. 4s2. And finally, the 3d orbitals have a total of 6 electrons. So hopefully this helps a little bit and puts things in perspective. Those bubbly shapes are great, but now we have like a bigger picture, like a better roadmap of where the electrons can be found in an atom.